Here we go with G6B. Rectifiers, solid-state diodes, transistors, vacuum tubes, and batteries. What's the peak inverse voltage rating of a rectifier? Okay, it's the maximum voltage the rectifier can handle in the non-conductive direction. And here's what we're talking about. Here we have a rectifier diode. Okay, and as the AC comes to this diode can only pass the electrons one direction. So as we have electrons moving this direction, they pass through the diode. As we have electrons moving the opposite direction here, they don't pass through the diode. That's the reverse voltage. And so we end up with something like this, with just the positive half of the cycle coming through that diode. And the peak inverse voltage rating of a rectifier is the maximum voltage the rectifier will handle in the non-conductive direction. In other words, the part that's been cut off here is the inverse, the peak inverse voltage. So that's what we're talking about. What are two major ratings that must not be exceeded for silicon conductor rectifiers? They're the peak inverse voltage, because if you exceed that rating, you will damage the junction of the diode, and the average forward current, because you'll overheat the diode if you exceed the current limit or the current rating for the diode. So these are the two major ratings that you must not exceed in designing a silicon diode rectifier. What's the approximate junction threshold voltage of a germanium diode? The two main materials that are used for making diodes are germanium and silicon. Here we're talking about a germanium diode, and the approximate junction threshold voltage of a germanium diode is 0.3 of a volt. The junction threshold is the lowest voltage at which the diode will begin to conduct. So a germanium diode has to have at least 0.3 of a volt on it before it will begin to conduct. When two or more diodes are connected in parallel to increase current handling capacity, what's the purpose of the resistor connected in series with each diode? The purpose is to ensure that one diode doesn't carry most of the current. Here you can see a diagram for this right here. Here are your two diodes connected in parallel, and here are the resistors that are put in series with them to help assure that one diode doesn't end up carrying all of the current, or a major portion of the current. What's the approximate junction threshold voltage of a conventional silicon diode? Here's the other material for diodes, and in the case of silicon, the threshold voltage is 0.7 of a volt. Here's what that would look like. We apply voltage to the diode, and finally here at 7, we finally get good conduction out of the diode. Okay, that can be used as a voltage regulator, as is shown here. Here we have a variable DC supply, and we have a resistor, a load resistor of some kind, and these 10 diodes will hold this voltage at this point to 7 volts because they conduct there. The resistor lowers the current, or the current through, let me start that again, the resistor, because of the increased current here, the resistor will control this at 7 volts out here at the terminals. Now, that's kind of a crude way to do voltage regulation, but I've actually used circuits that do it that way. And the silicon diodes will conduct at 0.7 of a volt. If you have 10 of them in series, then you have a 7-volt regulator. Which of the following is an advantage of using a Schottky diode as an RF switching circuit, or in an RF switching circuit, as compared to a standard silicon diode? The Schottky diodes have lower capacitance, which makes them more suitable for radio frequency circuits. What are the stable operating points for a bipolar transistor used as a switch in a logic circuit? A logic circuit is a digital circuit. It has two states, on and off. And the places where you want your transistor to operate are at the saturation and the cutoff regions, and that's what this looks like here. Here's a saturation region where the transistor is conducting 100%. Here's the cutoff region where it's conducting not at all. Okay, so those are your two regions that you operate in for a logic circuit using a bipolar transistor, saturation and cutoff regions. Why must the cases of some large power transistors be insulated from ground? The answer is to avoid shorting the collector or drain voltage to the ground, and that's because in many of these transistor case designs, the collector or the drain, if it's a field effect transistor, are connected directly to the case to help dissipate heat. And in this diagram here, you can see that the collector is the metal case, and the base and the emitter are these little wires that come sticking out through insulators there. Here you can see how that installation is done to insulate that from the chassis. The transistor is bolted with machine screws to the chassis, but you can see there's a mica washer here between the transistor and the chassis. Okay, there are also little insulating sleeves around the screws here so that the screws cannot touch the chassis, and this allows the chassis to take the heat from away from the transistor without making an electrical connection to the transistor. So that's why they need to be insulated from ground, to avoid shorting the collector or drain voltage to ground. The reason they're designed this way is so that they can dissipate the amount of heat that's generated in the power transistor. Which of the following describes the construction of a MOSFET? A MOSFET is a metallic oxide semiconductor field effect transistor. And I have a picture. The gate is separated from the channel with a thin insulating layer, and they have that. This isn't a really good diagram, but it's the best one I could find. The gate connector is here, the source is here, the drain is here, and this is the channel through which the electrons flow, and there's a very thin insulating material right here between the gate and the channel, and that is how it is constructed. Now, even though there's this thin insulating material here, the gate can still affect the flow of the electrons through the channel there. Which element of a triode vacuum tube is used to regulate the flow of electrons between the cathode and the plate? A tip-off here, if you happen to get this question, you have the word regulate here. You have the word control here. Similar in meaning, aren't they? And it's called the control grid. Okay? The diagram for the tube looks like this. You have a cathode that, when it's heated, will emit electrons that are attracted to the plate, so that you get a current flow of an electron flow this direction through the tube, from the plate to the or from the cathode to the plate. And the voltage on this control grid can help control how much current will flow through there. Okay? So the control grid will regulate the flow of electrons between the cathode and the plate. Here's the way it would be constructed in an actual tube. You'd have the plate out here on the outside. You'd have the cathode here on the inside with a heater inside, the filament inside to heat it, and then the grid. Which of the following solid-state devices is most like a vacuum tube in its general operating characteristics? Correct answer is a field effect transistor. Now, the design of it is nothing like the physical design of a tube, but characteristics like the impedance of the inputs and outputs and so on are closer to vacuum tube characteristics than other semiconductors are. What's the primary purpose of a screen grid in a vacuum tube? The triode that we just looked at did not have a screen grid. And it has a problem because if you look at this, you have a plate, you have a grid, and if you think about what the diagram for a capacitor looks like, that's kind of similar, isn't it? You have you have an electrode here, you have an electrode here, you have space in between, which is insulated, so there is capacitance between the two. By adding the screen grid in here, we can reduce that capacitance, which is desirable, especially as you get into higher frequency radio frequency circuits. So the purpose of the screen grid is to reduce the grid to plate capacitance. And you can think of this as just adding an additional capacitor in series with the capacitance that's already there between the grid and the plate. And you'll remember when you put capacitors in series, you reduce the capacitance. What's the advantage of a low internal resistance of a nickel-cadmium battery? All batteries have some internal resistance, and as current is taken from the battery or recharged back into the battery, that resistance will generate heat. The higher the current, the more heat, so the low internal resistance of a nickel-cadmium battery allows a high discharge current without the battery overheating. Low internal resistance allows a high discharge current. What's the minimum allowable discharge voltage for maximum life of a standard 12-volt lead-acid battery? A normal battery, normal car battery, should not be discharged below 10.5 volts. Now, deep cycle batteries can tolerate lower voltages than that, but your standard car batteries will begin to suffer if it's discharged below 10.5 volts. When is it acceptable to recharge a carbon-zinc primary cell? The carbon-zinc primary cells are the ones that you see at the store, called heavy-duty. It's the worst name in the world for them because they're not heavy-duty. The alkaline cells, the lithium cells, are all superior to these, and these should never be recharged.